All right. So, hello everyone again. Let us start for today. We are continuing what we sort of began to explore last time. But now introduction is over and we will start to get into the content of, of our course. But we will take it slow. So this lecture might also be pretty short. But at the same time, I would suggest you treat the ideas that I give you here seriously, because while they look simple, you have to apply them. So it's like it would be better if you understand how those ideas work directly. Okay. So this lecture is about constraints. What are constraints? Please notice it is not about like contact. That we'll see a bit later. It's about constraints, so it's a little bit simpler. Okay, so let me go into this. All right. So first, before we begin thinking about constraints, by the way, let me check, make sure that I have chat somewhere open. Just a second. I'm not sure where it is. Anyway, so before we begin with our constraints, let us remember what a dynamical system is. Well, for example, one way to represent it is as an ODE, okay? That's one simple way to express a dynamical system. Do you understand like this definition? Have you encountered it before? Have you seen a ODE in this form before?
Yeah, we've seen something like that, I think.
Mm-hmm. Okay, so from your answer, I judge it is still relatively new. Okay. Well, how should I put it? Every dynamical system, in general, as I said, means a ODE, ordinary differential equation. And ODE in general can be represented in this form. So it can be represented as x dot equal to f of x comma t. Okay. Why? If you remember what an ODE is, ODE includes a linear equation, like linear differential equations, non-linear differential equations. For example, pendulum equations are that we have here as an example. Those are second order equations, right? So how can you say that this is the general form? Does it make any sense? It feels like it doesn't, right? It feels like it is just a, how should I say it, special case. But in fact, it is a general case. So let me try to argue that it is on using an example. Okay, so example number one, we consider this dynamics, which is the dynamics of a pendulum, okay? Phi double dot in this case is the angular acceleration. Phi is angle relative to this position downwards of the pendulum, so it can move up a little bit. And angle relative to the vertical is phi. Okay. So what we can do is we can start with introducing a change of coordinates, phi dot, that is suggested here. Okay, so we can introduce a change of coordinates, and then we can write what dynamics would be in terms of those new coordinates. Well, the first coordinate is phi. What is it equal to? What its derivative is equal to? The first coordinate is phi. The derivative of phi is phi dot. So that is why we can see that x1 dot is equal to x2. That just follows from the definition of the new variables we introduced. Okay. Well, this should be clear. That is the important concept. I'm not saying that we have to do it a lot, but we need to understand this. So when we introduce this change of variables, our original one variable ODE become a two variable ODE, but where the first was the, how should I put it? First was the second order differential equation. After that, we get the first order differential equation. It is nonlinear still. And of course, the original was nonlinear. And the nonlinearity is not a matter of representation, it is a matter of geometry. So of course, it would still be nonlinear. Where is the nonlinear part? Well, it is here. You can see L times sine of x1. That is a nonlinear part. Make sense so far? All's clear?
Yes.
Make sure you ask questions before I move on. I mean, or whenever it is convenient for you. Okay, so the example was just to show that the form number one is the general enough form. So we can use it every time we want to discuss a dynamical system. And so, okay. Now about constraints. So a constraint is equality that must hold for the dynamical system for the whole time during its motion. So how should I say it? This is inequality that is always true for this dynamical system. That maybe sounds simple, but there is a lot of context with it. So let us look into, just to understand this better, let us look into this dynamical system. Okay. And we will require that this dynamical system has this constraint. What does it mean? Well, it means that while here we say that, x changes only with respect to what f is like, right? And f depends only on the state and time. So, it kind of feels like x just depends on x and maybe on time. Well, that is, of course, that's normal geometry of differential equations. But now somehow we require that this expression is true. So the first expression should actually be somehow such that this next expression holds. That is not clear how you achieve this, right? It is not clear from the formulation why that would be the case. Okay. And indeed, if you just ask, you come to a differential equation and ask it, please make sure that this equality holds, it's not going to hold. So constraints are not just magical things. You cannot just add them to your equation and make it hold, right? You need to do some work to make sure it holds. But that's the idea. That's the general idea of what a constraint is. Now, we can also ask a constraint to be of this form. G of x comma x dot. So in this case, it will be pretty much a differential equation. It can be a degenerate differential equation. So it doesn't have to be solvable with respect to x dot. Unlike here you can see it is solved with respect to x dot. So x dot is separated on the left-hand side. Here it doesn't have to be separated on the left-hand side. It doesn't have, no requirements. It is, can be degenerate with respect to x dot. Okay. And that would be just a different form of constraints. And indeed, we will find constraints of this form often enough. We'll call them differential because they require you to use differential, they require you to have derivatives of the variables there. Whereas here, at least in this representation, it doesn't have them. Okay. Both constraints are found easily enough, and one can be transformed to the other. So this one point, let me just give you a suggestion to think about. So let's say you want to take this guy and differentiate it with respect to time. What is the way to differentiate it? I suggest chain rule. Can someone tell me what would be the derivative of this guy using chain rule? Mathematicians in the chat, please. Really? No answer? Come on.
Why we need to compute it?
Just ask to compute it. Find the derivative of g with respect to time.
It is 0.
Why?
Because this constraint always holds, and as we want to have it like that.
Well,
it will not change over time.
That is, I'm glad we have this discussion already. So this is a very important conceptual point. So indeed, we know what the value of this expression is. So this expression here has a value 0, okay? Always. So you know that the derivative of this expression indeed has to be equal to 0. Why? Because it doesn't change. Or why? Because derivative of 0 is 0, okay? But, there is a difference between asking what the expression is equal to when you evaluate it and what the form of the expression is. So let me just give one example if I can. Let me just see if I can try to start annotation. Oh, we haven't answered the chat from a master student. Very interesting. I'm not going to comment on it, but good job, Ramil. Okay, good job. So let me just say this, okay? So imagine you have this expression. Oops. Cosine x squared plus sine x squared. Okay. You know what this is equal to? Someone answer. What?
1.
1, yes. Yes, yes, yes. Good. Now, can you find me derivative of the expression on the left-hand side? I mean, come on, it's very simple, right?
Minus 2 sine of x plus 2 cosine of x.
Sounds incorrect, actually. Like, it should be, first, it should be 2 cosine x, right? When we take a derivative of the square.
Yes.
Times minus sine x, right?
Yeah.
Plus 2 sine x, right? Times cosine x. Something like this, right?
Mhm.
Now, what is this equal to?
0.
Yes. How did you know?
Because we have two same values with different signs.
Oh, really? So you noticed that the expression itself, the expression here is symmetrical and should evaluate to 0. That is impressive. Good job. But I knew that it was 0 without looking at the expression, because I know if you differentiate 1, you will have 0, right? And that was your original argument for this case. So you see, like what you said originally about the constraint is smart. It allows you to, for example, evaluate this expression without looking at the symmetry. But this time you did look at the expression and found its geometry very obvious. So good job. Now, what I'm so what I'm trying to do here with this expression, with asking you to differentiate this expression, is I just want you to provide me a form of how this derivative will look like. I know what it is equal to. It is equal to 0, but I need to see the form. So can someone tell me? I mean, probably you saw the answer in the chat. So yeah. I guess I will still just, how should I say it? I'll just write it here. Chain rule is partial g partial x. I don't have a partial symbol on the standard keyboard, so I apologize, but partial g partial x times x dot, so basically dx dt. So this is the form of the derivative of this guy. We're using chain rule. You take derivative of g with respect to x and derivative of x with respect to time. Okay. So this is now, why did they spend time on this? Well, because look, please, here. Do you see something? You see x dot, right? Look here now. See x dot? In other words, simply differentiating a algebraic constraint, you get a differential constraint. So please don't treat them as kind of beasts from completely different, genera. They are from, the same family. And you can get one from another. Okay, good. Now, if I can clear all this. Good. So, apologize for it's a little bit difficult to move all those annotations around. All right, so let us look into an example. So I remember last time we saw a double oscillator. Okay. By the way, in the homework, I asked you to provide a dynamics of the double oscillator, I think. But you had to do it probably in terms of an ODE. Here is not an answer to your homework, just to be clear. Okay, so double oscillator has the form shown here. That is the dynamics that is given for you. You hopefully remember what those mean. Let me just quickly recap. Those are mass, the stiffness coefficient of the spring. This is a rest length of the spring. But now we introduce external forces, F1 and X2. Okay. Good. Now, what I want to do is I want to require that this constraint holds. Just want to make sure it works. So this constraint holds. Meaning that distance between those two bodies should be equal to 1. So I added, like the equation changed. I just added this algebraic equation at the bottom. But so far, there's absolutely no reason why it would be true. So in fact, while, how should I say it? How do you interpret mathematically expression 6? Well, expression 6 says, is basically like those simultaneous expressions, systems of expressions, they usually mean intersection, okay? So let's say you have an expression like x1 plus x2 equal to 1. What is this expression? Well, if there are only two variables, x1 and x2, then it defines a line, okay? If you have a system of expressions and one is x1 plus x2 equal to 1, and another one is x1 minus x2 equal to -7, then it is intersection of two lines, one defined by the first expression, one defined by the second expression, and it is a point, okay? All right, so what here is this part? Can someone tell me? Well, geometrically, it talks about two variables and their first derivatives. The second derivative is, I mean, that is a little bit beyond what you taught before, but you can think about the second derivative as a vector field that defines completely how the first derivative and x itself is going to change through time. So in fact, you have a 4-dimensional space here, x1, x2, x1 dot, x2 dot, okay? That's your plane on your hyperspace on which you exist, okay? Now, those two equations, what they define is how you can propagate from initial condition to the final condition. And that in fact will be a single line, single curve. It's not going to be a plane, it's not going to be a volume, it's going to be a curve, one-dimensional object. Can someone tell me why? Why is this expression that I boxed defines a one-dimensional curve rather than a plane or something else? Can someone tell me? And that is, of course, a very high-level question. But you'll feel very good if you answer. So,
can you repeat the last sentence?
So this boxed equation in the red box is defining a curve, which is one-dimensional object in this four-dimensional space. Four-dimensional space is of x1, x2, x1 dot, x2 dot. And those two equations give you a one-dimensional curve in this space. So y. Curve that explains how the,
because we have constraints that which connect x1 and x2.
No. I'm completely excluding the last third equation. I'm only talking about the first two equations. So let me give you the answer, because those are, don't want to dwell on it too much because those abstract thinking without illustrations is hard. But let me explain it, in simple terms. How many solutions does this equation have, given initial conditions? If I give you initial conditions, how many, how would solution of this equation look like, basically? A function of time. That's what it would be. It will be one function of time. So the solution of this equation cannot, is not a plane, is not a volume. It is a function of time, okay? It maps time to four variables, x1, x2, x1 dot, x2 dot. That's it. That is what solutions to all ordinary differential equations actually are. If you think about it, they are curves. If you can come up with an equation whose solution is a plane, that is very interesting. I mean, of course, I can, how should I say it? I can get you an example kind of like this in a moment, but it would be a little bit of a cheating. But anyway, for equations like this, where they, how should I put it? They exist in this four-dimensional space, and they completely define how those four variables evolve. The solution will be a curve. Of course, the exact curve depends on the initial conditions, but that doesn't matter. So far, I'm just trying to say that this is a one-dimensional object. Okay, good. Now, what is this guy? Well, this guy, can someone answer instantly what is the geometry of this guy in this four-dimensional space?
Well, the last one.
One option was line. Second was what? Aidar, you said line. Evgeny, you said what?
I asked whether you're talking about the last equation.
Yeah, the last equation. Yeah, the last one.
The line.
No, it's not a line. Why did you think it would be a line? Because because in the two-dimensional example, it is a line? No, of course not.
It will be like a point. It is a point. It's
No, it's
in
not,
one dimension.
Not a point.
Oh, okay.
There is a very easy, for linear algebra at least, there is a very easy, just, how should I say it, rule to find what the geometry of such objects is. Basically, any equation takes away dimensionality of the space. And, that's it. How many dimensions does this equation take from the space? One. This takes one dimension, the third one, because it just says that whatever x1 and x2 are, they better stay within interval of 1 from one another. But they say nothing about x1 dot and x2 dot. So All right, so this is actually a hyperplane, three-dimensional hyperplane in the four-dimensional space. That is what the third equation is. It describes a three-dimensional hyperplane. Sounds scary, maybe, because it's hyperplane, right, in four-dimensional space. Wow. But actually it is, it's just the x1 minus x2 equal to 1. That's all there is to it. But it sounds fancy. And the reason I'm bringing this up, that it is a three-dimensional hyperplane in a four-dimensional space, is because, if you want to imagine how it looks like, think about a two-dimensional plane in three-dimensional space. Of course, it is a bad analogy in a sense, but what the main point is, it lacks one dimension, okay? Now, imagine now intersection of this one-dimensional curve here, and this three-dimensional hyperplane here. What would be the dimensionality of the intersection? What do you think? That is actually, now that is a difficult question. Go ahead, Evgeny.
The intersection is 2D plane.
Excuse me, sorry?
The intersection of these two things is 2D plane.
2D plane? No, I mean, it cannot be. Because the definition of intersection is the points that belong to both of the original objects. And one of the objects is a one-dimensional body. So it cannot possibly increase the dimensionality. Okay, let me, I don't want to confuse you too much. Let me try to explain. There can be cases, right? For example, this curve, let me just clear all this. So for example, this curve can actually lie completely in the hyperplane. It can, right? Just can happen. Then the intersection will be the curve. On the other hand, this curve can also punch through the hyperplane. Okay, hyperplane is three-dimensional, but remember, this ambient space is four-dimensional. So the curve can go and just right through this hyperplane. What would it mean? It would mean that it has a point where this holds, but for most of the points it doesn't hold. So that is the second option, and most likely. So the most likely option is, because the chance that it would randomly just lie on this hyperplane is 1 to infinity, so 0. It can happen, which is funny, like the chance of it happening randomly is 0, but it can happen. That is, if this confuses you, statistics is maybe something you can try to study for a hobby. They have a lot of those confusing stuff, but yeah, that is true. The random chance of randomly generating a curve like this is 0, but you can artificially generate one. Okay, now answer to my question is one-dimensional body. So intersection of this curve with this hyperplane is one-dimensional. Now, why did we spend so much time on it? Well, because now you can answer my next question very easily. If this intersection is indeed one-dimensional, is it a solution to any ordinary differential equation? Oh, sorry, zero-dimensional. I said one-dimensional. Sorry, I was wrong. Sorry. It is zero-dimensional, so it is a point, all right? Point has 0 dimensions, 0 degrees of freedom. So if the intersection of this curve and this hyperplane is 0-dimensional, can be a solution of a differential equation.
no, because when we have differential equations, it's some function over time, which in general case can change. And but if we have a point, there is
No change, right?
no changes.
Yep. I mean, you can put it even simpler. You can say, because the solution to differential equation is a curve, one-dimensional curve. And indeed, in some cases, special cases, this curve can be degenerate and be a point. But then this means, so this can happen. But in general, it is not the case. But however, let me again point out, if this guy is lying on this hyperplane, just happens, then indeed it is a solution to a differential equation. Okay, we belabored this enough. I hope you understand that just introducing a constraint basically would most likely lead to you, instead of having a solution to a differential equation, you just get the point. That is what the geometry of this mathematical expression is. Okay, now, oops. So what we can do now is we can decide to differentiate this constraint. Okay, notice we differentiated it twice. What did we achieve? Well, we achieved that instead of having an algebraic equation, which, as we said, was a hyperplane in the four-dimensional space, we now have just additional variables of our higher order derivatives. So this doesn't restrict actually our solution space. So we no longer have a hyperplane. Now we have something different. This guy boxed here restricts now the values of this part here, because this part defines what x1 and x2 will be like. And this equation down below restricts that, okay? You see the difference. Originally, we restricted a four-dimensional space of state variables. Now we are restricting a two-dimensional space of accelerations. And we achieved it by differentiating the constraint twice, okay? But also I would like you to notice that, just because we want to restrict this right-hand side, sorry, is not going to be restricted. So what most likely we will get from this restriction is inconsistent equation. So equation with no solution. Does it make sense what I said?
I have a question.
Yes.
So in first, when we talk that the first equation it's a curve in represent one D curve. So when we put these differential constraints, so the result it will be another curve that we bounded, for example, with these constraints as a result.
You are talking about the expression 7, right?
Yes.
So expression 7 would ideally be another curve. But what I'm trying to say right now is that in general case, it's not going to be anything. It's going to be an inconsistent equation.
Okay.
But your idea is very correct, but we'll get to illustrate it in like 1 or 2 slides. So
okay.
Thank you for the question. Good. Now, does it make sense that right-hand side of this equation and the constraint might not be consistent? That in general, it just may happen that, just doesn't hold? Well, I think next slide might be illustrating it better. Oh, no, not next slide, doesn't. Okay, we'll see it in a moment, but let me just give you one suggestion. Imagine that K1 is equal to 0. And imagine that K2 is equal to 0. Okay. Now, imagine that M1 and M2 are equal to 1. What do you see? You see that X1 double dot is equal to F1. X2 double dot is equal to F2. Okay, makes sense? Now, what if F, let me try to use annotation. What if F1 is equal to 10? No, 10, right? And what if F2 is equal to 1? Well, you can clearly see that X1 double dot minus X2 double dot are not equal to 0, right? So what that is a problem, right? And you can see that essentially the system of equations has no solution. So it doesn't mean anything. It doesn't describe a geometrical object. That was my point. Okay. Okay, I assume it is clear. Now let me move on, if I can. Okay. Now, let us add a force lambda acting on the first equation. Why do I add it? Well, I just want to make sure that there is always a variable that can ensure that this equation will hold. Okay? That is not coming from physics for now. That is just, I want something to make sure that this equation, this constraint holds. By the way, that is a legit technique. So, you know, take notice. That is, you know, sometimes people call it Lagrange multipliers method. You see it in optimization, in mechanics, in probably everywhere where you have to deal with constraints. Okay, so all right. So I just added this force, but by the way, just one more thing. While this, you know, how I should say it, Lagrange multipliers method is actually more specific. What I did here is like a hooligan street way of you know, making this Lagrange multipliers. That's like not how classical approach works. But anyway, okay. So here is the force that I added. Now is the question: is it always possible now to make sure the constraint holds? Well, I claim yes. Let me show why. Well, let us do exactly what I did before. Introduce those new values for our constants. And then we have this simplified system of equations. Now, we see from this system of equation that x double dot, x2 double dot is equal to f2, correct? Right? I mean, obvious. Now, from this system of equation, we know that x1 double dot equals to x2 double dot, and therefore is also equal to f2. So that is noticed here. Okay, so it's just a conclusion from equations. Now, in order for this to be true, lambda has to be equal to this guy, right? I know this by looking to this equation. I know what x1 is. X1 double dot is equal to f2. So for this equation to hold, I need lambda to be what I wrote it to be. Makes sense? What I just did? Just algebra, right? Now, look here. So the work produced by the force lambda, since we know what its value is, we just need to multiply it by x1 dot, basically. I mean, let us even not like concentrate on the exact value of this expression. Basically, what I'm just trying to say is this, the idea of bringing like just a random idea of a force or work into discussion of general ODEs is strange. But this was a double oscillator. That is how I am able to do it, because I know this is a force basically acting on the first body, so I know what the work would be like. Just integral of a power, so of a velocity times force, and that expression that I get for the mechanical idea of a work is not zero in general. What it means is that regardless of the constraints, regardless of what the constraints are like, it is still no, let me try to start over. So it means that this force is not only stopping us from violating the constraint, it also shapes how we move, because it introduces energy into the system by doing work, or it takes away the energy from the system by doing negative work. That is the idea. It influences how the system moves, not just prevents us from violating the constraints, because not violating the constraints constitutes a zero movement. Work into the direction of violating this constraint is always zero. Why? Because imagine this constraint is like this curve. Okay, well, violating constraints means moving this way, but we don't do it. Okay, so our force, if it only prevents us from going there, it kind of acts in the same direction, but there is no movement in this direction. So we know the definition of work is a movement, like how far you moved times how much force was applied, and you moved zero. So no matter how much of a force you applied, your work is zero. That's the idea. So that is why a constraint that only acts on preventing you from violating, force that only acts you on preventing the violation of constraint would have zero work. But this one doesn't. This one has a non-zero work in general. So it actually shapes the dynamics of the system. And that's what Aidar, I think, kind of like was getting to. This expression here is a new differential equation. It indeed has a trajectory. It's a different trajectory from original double oscillator, but it has a trajectory in space. It is a curve. Now, because we added this lambda, this would just be a one-dimensional curve in the solution space. That's it. Of course, since x double dot 1 equals to x double dot 2, we could have actually completely ignored one of those variables because it doesn't actually make sense. For example, x1, we can completely ignore it. The whole system is completely described by x2 double dot. And the other variables are just there, they can be gotten from algebraic relations between those two variables. But that is, that is a matter of taste or representation or whatever. We don't just ignore variables in algebra when they are algebraically connected. So we don't have to ignore them here. Okay, hope it wasn't too abstract. Did it make sense to anyone, what we talked about? Need your feedback. Did it make sense?
Yeah, now clear.
Okay. All right. It will get better in a bit.
Yeah.
Okay. So now let me construct you a force which will not introduce work into the system, which will do zero work. Well, by the way, those forces, we can call them reaction forces. This is a convention. Force that prevents you from violating a constraint is, nice to call it a reaction force. Okay, now, so some people in mechanics might require that reaction force produces no work. So when you have a reaction force like in the previous slide, be careful. But if your force produces no work, you can easily call it reaction force. Okay, so now I introduce it this way. Minus lambda plus lambda. Completely randomly, right? It's like, how did you choose this? I can tell you how I chose it sometime, but not today, because it would require you to think about something called a row space or a null space, which we'll get to in a bit, but not today. You could also do it using your ingenuity, of course. Of course. Okay, sorry. This reaction force would be equal to, if you calculate it, to this thing. So I ask you to prove it as part of your homework. And, it's very easy actually to prove it. Can someone give me an idea how they would try to prove this? How they would try to find lambda? What is our lambda equal to? Someone? Expression 10, how would you find lambda?
We just apply the constraint which we have in the third equation.
Yep. How do you apply it?
We can, for example, substitute x1 on. We have constraints that x1.
Yeah. Substitute was good word. I mean, you don't need to use apply constraints. That is like it's already applied. Substitute. Yeah, you use substitution, right? That's a very correct term. What you're saying, you substitute one of those x1 or x2, then you get two system of equations with two unknowns, lambda and one of the derivatives, right?
And we can, for example, we get the equation that x2 equal x2 dot equal f1 minus lambda, and x2 dot equal f2. And finally, we will get equations that f1 minus lambda equal to f2 plus lambda. And then we can get the final.
Right. Great. That is very nice. So you propose substitution. That's good. You can also just say, you know, like if someone asked me, what I would say is less helpful than what you said. You just gave a complete recipe. I would just say, you know, solve a linear system of equations with x1 double dot, x2 double dot, and lambda. You know, that is a matrix. You with you know, just a normal matrix equation. You just solve it by inverting the matrix. But of course, like your substitution way is just way more, you know, visceral and easy to understand. So thank you. Very good. By the way, you could also, after the first substitution, just subtract second equation from the first. Would also work. But anyway, now that is how you can get a lambda. That's your homework, please. Do it. Now, the force, the work produced by this force is now, let me clear it, is now this form. Well, you can recognize that I just multiplied this for lambda by x1 dot with a minus sign, and the same by x2 dot with a plus sign, and I summed them. And the total work, as you can see, would be equal to 0 as long as this constraint holds. And this constraint will hold as long as the initial condition for x1 and x2, as long as this holds initially, this will always hold because of this guy. But remember, our original constraint even requested that the state remains the same. So we just can assume that initial condition is such that initial conditions are such that this is indeed true. Because in the original problem we have, how should I say it? Let me be more careful. We shouldn't just randomly assume stuff, right? But instead we should say, if this assumption holds, then this result holds. The result is this is equal to 0. That's the correct way. But this assumption is reasonable, is what I'm trying to say. Okay. Now, now what we proved, just you know, with you, is that lambda is producing all work. How did we get there? Well, please notice that we get there by choosing this very specific distribution of reaction forces. I just gave it to you. How did I get it? I didn't tell, but there is a method. Okay. So let me just check. Let me just check where. Okay. So now what I want you to think about is this. Imagine you have a mechanical system, like a robot arm. This robot arm has to contact some surface, okay? It contacts the surface. Now, you can, for mechanics, remember that there is an expression, you know, there is a way to describe those situations using like reaction forces and whatnot. But now I'm suggesting, you know, let's think about constraints it introduces. So we know that end effector, which is a, you know, its position is a function of cosine, sines, etc. You know, end effector. So the end effector will stay in contact with the wall. How do you introduce those lambdas, reaction forces, in such a way that they will produce no work? We know that mechanical systems produce no work. Mechanical systems constraints produce no work. That is, we know it from classical mechanics. Maybe we'll prove it, I don't know, in the coming lecture. How do we introduce them? I just want you to think about it for a while, maybe like after the lecture. That is a fascinating topic because like mechanics gives you rules how to generate those equations, but you don't have to follow the rules of mechanics. You can also just generally think about it in terms of ODEs. Because, for example, if you go into virtual constraints or virtual mechanics, stuff that, for example, Slotin, one of the MIT leading researchers, is actively pushing, you don't necessarily have mechanical rules, but it is nice if you understand how those things are being made. So here, again, as I just said, I use the method, how to do it. I will show you this method once we get to, once we pass the prerequisites for it. But just think about it for yourself. How would you add those constraints in a meaningful way? All right. Now, that is it for the introduction of constraints. I hope it wasn't too hard, or I hope you didn't fall asleep. I know it was a little bit dry, and to be honest, there is how I should say it. There is a lot of this prerequisite material which it's like not as exciting as it is pedantic or conceptual or whatever. But you learn very good things from it. So please tough it through. It's good. Like the knowledge you got today, if you didn't know, like the idea of constraints was a little bit new to you, is good. It will build on it in the coming lectures. So, and like tomorrow we'll have a huge dive into mechanics. It will probably look a little bit scary, but I hope you stick with us, like with me, with the group. And even though it is scary, and today was conceptual, tomorrow, next lecture, it will be hugely theoretical. It will be useful though, useful for understanding. One of the key ideas of this course for me was to make sure you have a complete picture. It's very easy to give this topic as a, please refer to the mechanics for this part, I'm just giving to you. Please refer to optimization for this part, I'm just giving to you, etc. Instead here, I wanted to give you foundations and in an intuitive way. So apologize for conceptual lectures like this. But anyway, now your homework. As I said, first prove this guy. Simple enough, right? Now, this second one is a difficult homework, but doable, of course. So for this system, introduce reaction forces, which enforce constraint that they have written, and try to make sure it produces no work. Think about it as a two-body system. So think about this system 11 as describing two bodies which are completely independent, with a force acting on one body, a force acting on the other body, and three-body system, and there is a third body here. And the stage it goes with a constant acceleration of 1. So apologize, someone is so that's it for that's it for the instruction, I guess. We'll see each other in a bit. I'm not going to end the call. We'll be back, but I will stop the recording.